There are more stars in the universe than grains of sand on every beach on Earth. That sounds like a dramatic line people throw around in documentaries, but when you actually think about it, it becomes disturbing in the best possible way. Every beach. Every coastline. Every desert edge. Every hidden island nobody's ever walked across. And even after counting all of that, we still wouldn't come close to the number of stars that exist in the observable universe. Our galaxy alone contains hundreds of billions of stars, and beyond the Milky Way are billions of other galaxies stretching farther into darkness than the human mind can comfortably process. For most of history, humanity looked up at all of it and asked the same question: are we alone? Not philosophically. Not spiritually. Literally. Is there life somewhere else out there in the dark? Because if the answer is yes, then humanity is not the universe becoming conscious for the first time. We are simply one species among many in a cosmos already alive. For thousands of years, that question remained impossible to answer. We could observe stars, map constellations, predict eclipses, and eventually understand gravity, but planets around other stars stayed hidden. A planet does not generate its own visible light the way a star does. It reflects light. Trying to detect one from Earth is like trying to photograph a grain of dust floating beside a stadium floodlight from thousands of miles away. For a long time, scientists believed finding planets outside our solar system would remain nearly impossible. Then technology changed everything. Over the last few decades, astronomy entered an entirely new era. Humanity stopped imagining planets around distant stars and started discovering them by the thousands. Massive gas giants larger than Jupiter. Frozen rogue planets drifting through interstellar darkness without stars at all. Lava worlds with oceans of molten rock. Water worlds. Super-Earths. Entire systems stranger than science fiction ever predicted. But among all of those discoveries, one system stood apart from the rest. Not because it was the largest. Not because it was the nearest. But because it looked strangely familiar. 40 light-years away from Earth, hidden inside the constellation Aquarius, sits a tiny dim red star known as TRAPPIST-1. Orbiting that star are 7 rocky planets. Not gas giants. Not frozen ice balls. Rocky worlds roughly the size of Earth. Several of them orbit inside the region where temperatures may allow liquid water to exist. And no other planetary system we have ever discovered looks quite like it. 7 Earth-sized planets around one star. Packed together tightly enough that from the surface of one world, neighboring planets could appear larger in the sky than our moon appears from Earth. The moment astronomers confirmed the system existed, TRAPPIST-1 became one of the most important places in modern science. Because for the first time, humanity had discovered not just one potentially habitable world, but an entire collection of them. It felt less like finding a single oasis in the desert and more like discovering an entirely new continent. But before we talk about the planets themselves, we need to understand the star they orbit. Because TRAPPIST-1 is nothing like our Sun. Our Sun is enormous. Violent. Blindingly bright. It dominates everything in our solar system. TRAPPIST-1 is tiny by comparison. It belongs to a class of stars known as ultra-cool red dwarfs. Its radius is barely larger than Jupiter's. Imagine that for a second. A star only slightly bigger than a planet. Its surface temperature is dramatically lower than the Sun's, glowing a deep reddish-orange instead of bright yellow-white. If Earth orbited TRAPPIST-1 at the same distance we orbit the Sun, our world would freeze solid almost instantly. That creates a strange situation. Because the star is so dim, planets need to orbit extremely close to receive enough warmth for liquid water. Much closer than Mercury orbits our Sun. And when planets orbit that close, gravity starts causing problems. One of the biggest is tidal locking. Over time, the star's gravity can force a planet into a permanent orientation where one side always faces the star while the other side remains in eternal darkness. No sunrise. No sunset. One hemisphere trapped in endless daylight while the other freezes beneath an unchanging night sky. Early scientists believed this automatically made red dwarf planets uninhabitable. The day side would become a scorched wasteland while the night side froze cold enough for atmospheric gases to collapse onto the surface as ice. But later research complicated that picture. Climate simulations showed that if a planet has a thick enough atmosphere, heat can circulate around the globe. Winds and ocean currents can transport warmth from the day side to the night side, stabilizing temperatures enough for liquid water to survive. Suddenly tidal locking no longer guaranteed death. In fact, some models suggested tidally locked worlds might still support enormous habitable regions. That realization completely transformed the search for alien life because red dwarfs are everywhere. They are by far the most common type of star in the galaxy. Most stars in the Milky Way are red dwarfs. Even our nearest stellar neighbor, Proxima Centauri, belongs to that category. If planets around red dwarfs can support life, then habitable worlds may be vastly more common than we once believed. But there's another problem. Red dwarfs are unstable. Especially when they're young. They erupt constantly with violent stellar flares that blast radiation into surrounding space. Some flares are powerful enough to strip atmospheres away from nearby planets over millions of years. And because habitable zone planets orbit extremely close to red dwarfs, they absorb the full force of those eruptions. A world can spend billions of years being hammered by radiation intense enough to destroy the very atmosphere life depends on. That's why many scientists originally believed red dwarf systems were terrible candidates for life. Too violent. Too chaotic. Too dangerous. Then TRAPPIST-1 changed the conversation. Compared to many red dwarfs, TRAPPIST-1 appears unusually calm. Not calm by Earth standards, but calmer than expected for a star of its type. Its flare activity is lower than many similar stars. Still dangerous. Still active. But potentially survivable. And that single detail made astronomers pay attention. The system itself remained unknown until 2016 when a robotic telescope in Chile noticed something strange. The star's brightness kept dipping at regular intervals. Tiny decreases in light repeating over and over again. That pattern usually means only one thing: planets passing in front of the star. The technique is called transit photometry. When a planet crosses between its star and Earth, it blocks a tiny fraction of the starlight. Sensitive instruments can detect those dips in brightness. By studying the timing and depth of the transits, astronomers can determine the planet's size, orbit, and sometimes even hints about its atmosphere. At first, scientists identified 3 planets. That alone was exciting. But further observations revealed something astonishing. There weren't 3 planets. There were 7. 7 rocky worlds orbiting the same star. And unlike many exoplanets discovered before them, these were not giant gas planets. They were terrestrial worlds similar in size to Earth. That distinction matters enormously because rocky planets provide solid surfaces where chemistry can happen. Where oceans can form. Where life as we understand it might emerge. Almost overnight, TRAPPIST-1 became one of the most important targets in astronomy. Then came the next breakthrough, the James Webb Space Telescope. JWST is not simply another telescope. It is one of the most advanced scientific instruments humanity has ever constructed. Its giant segmented mirror and ultra-sensitive infrared instruments allow it to analyze light with astonishing precision. And for exoplanet science, that changed everything. Finding planets is one thing. Studying their atmospheres is another. Atmospheres determine whether planets are frozen deserts, runaway greenhouse hellscapes, or potentially habitable worlds. Without an atmosphere, radiation reaches the surface directly and temperatures swing to extremes. Too much atmosphere can trap heat so efficiently that oceans boil away entirely. The right atmospheric balance changes everything. Webb studies atmospheres using a method called transmission spectroscopy. When a planet passes in front of its star, a tiny fraction of starlight travels through the planet's atmosphere before reaching us. Different gases absorb specific wavelengths of light. Carbon dioxide leaves one signature. Methane leaves another. Water vapor leaves another. By studying which wavelengths disappear during a transit, scientists can determine which gases exist in the atmosphere. It's essentially atmospheric fingerprinting across 40 light-years of space. And TRAPPIST-1 turned out to be almost perfect for this technique. Because the star is small and dim, planets block a much larger percentage of its light during transits compared to planets orbiting larger stars. That produces stronger signals and more precise measurements. Astronomers realized something extraordinary was now possible. Humanity could potentially study the atmospheres of Earth-sized worlds orbiting another star. And when Webb finally began observing the TRAPPIST-1 system, expectations were enormous. Some scientists hoped for signs of thick atmospheres and water vapor. Others feared the planets had already been stripped bare by radiation long ago. Nobody knew what Webb would find. What came back surprised almost everyone. Some planets looked worse than expected. Others looked more promising. And one world in particular began attracting serious attention from scientists around the globe. The first planet in the TRAPPIST-1 system is called TRAPPIST-1b, and the moment astronomers started studying it seriously, most hopes for habitability disappeared almost immediately. This planet orbits unbelievably close to its star, only about 1 million miles away. To put that into perspective, Mercury sits roughly 36 million miles from the Sun. TRAPPIST-1b completes an entire year in less than 2 Earth days. Imagine celebrating New Year's Eve every 36 hours. That is how fast this world moves around its star. Despite orbiting a dim red dwarf, the planet receives an enormous amount of radiation because of that close distance. Early models predicted that TRAPPIST-1b might resemble Venus: thick atmosphere, crushing pressure, runaway greenhouse heating, and temperatures hot enough to melt lead. Scientists expected a world wrapped in dense carbon dioxide clouds. Then the James Webb Space Telescope measured the planet's thermal emissions. And the results completely changed the picture. The day-side temperature turned out to be far lower than expected for a thick atmosphere planet. Still scorching hot by human standards, but nowhere near hot enough for the Venus-like scenario astronomers predicted. That finding suggested something important: the atmosphere probably isn't there anymore. Instead of a thick blanket trapping heat, TRAPPIST-1b now appears to be a bare rock directly exposed to stellar radiation. No clouds. No weather. No oceans. No meaningful atmosphere capable of redistributing heat. One side permanently facing the star and baking beneath endless daylight while the other side sits frozen in darkness. And that discovery mattered far beyond a single planet. Because if the innermost planets around red dwarfs lose their atmospheres this easily, then many worlds across the galaxy may already be sterile before life ever has a chance to begin. Next comes TRAPPIST-1c. At first glance, Planet C looked slightly more promising. It orbits farther from the star than Planet B and receives somewhat less radiation. It's slightly larger than Earth with almost identical surface gravity, meaning a human standing there would feel nearly normal weight underfoot. Scientists originally imagined a world covered in thick steam atmospheres or dense water vapor clouds. But once again, Webb complicated the story. The infrared data coming from Planet C revealed a world cooler than expected under greenhouse models. And just like Planet B, that strongly suggested the atmosphere had either been stripped away or was extremely thin. Possibly thinner than the atmosphere on Mars. That's a devastating result for habitability. Mars itself barely qualifies as having an atmosphere at all. Surface pressure there is less than 1% of Earth's. Liquid water cannot remain stable for long because the pressure is too low. If TRAPPIST-1c has an atmosphere even thinner than Mars, then the planet is effectively exposed directly to space. Astronomers also found something else troubling. There were no strong signs of water vapor. That may mean Planet C formed dry from the beginning, without significant amounts of water trapped inside it. And without water, biology becomes dramatically harder. At this point, early excitement surrounding the system started cooling down. 2 planets examined. 2 likely barren worlds. And suddenly scientists began wondering whether red dwarf systems were even capable of producing habitable planets at all. Then attention shifted toward the 3rd planet, TRAPPIST-1d. And that's where things became far more complicated. Planet D sits near the inner edge of the habitable zone. It receives roughly the same amount of stellar energy Earth receives from the Sun, only slightly more. On paper, that places it in one of the most interesting positions in the entire system. Physically, the planet is smaller than Earth and has lower gravity, somewhere between Earth and Mars. A human standing there would feel lighter, but not dramatically so. The world itself is probably tidally locked like the others, meaning one hemisphere constantly faces the star while the opposite side remains trapped in permanent night. When Webb began analyzing TRAPPIST-1d, scientists hoped they might finally detect a stable atmosphere. Instead, they got uncertainty. The observations were consistent with a planet that might have no atmosphere at all. But unlike planets B and C, the evidence was not strong enough to completely rule out alternatives. There remained the possibility of a thin atmosphere or even a thick volatile layer difficult for Webb to detect directly. That distinction matters enormously. Because atmospheres on these planets behave differently than atmospheres on Earth. If TRAPPIST-1d possesses a dense enough atmosphere, heat could circulate around the globe efficiently enough to prevent the night side from freezing solid. In that scenario, oceans might survive. Weather systems could exist. Clouds might drift across the twilight boundary separating eternal day from eternal night. Scientists sometimes call that region the terminator zone. A permanent ring of sunset circling the planet. Not day. Not night. A twilight world where temperatures might remain stable enough for liquid water. Imagine standing there. The star hanging motionless near the horizon forever. One side of the sky glowing deep orange-red while darkness stretches endlessly behind you. Winds roaring between hot and cold hemispheres. Frozen landscapes existing only a few hundred miles away from regions warm enough for rain. If life exists on tidally locked planets, environments like that may be where it survives. And there's another possibility that keeps astronomers interested in TRAPPIST-1d. The planet may contain enormous quantities of water. Some models suggest oceans potentially hundreds of times deeper than Earth's oceans. Others suggest thick steam atmospheres similar to a pressure cooker. At the moment, scientists simply do not know. And that uncertainty is becoming a pattern throughout the TRAPPIST-1 system. The farther outward astronomers look, the stranger these worlds become. Next comes TRAPPIST-1e. The planet many scientists now consider one of the most important exoplanets ever discovered. But before we get there, we need to talk about something critical: habitability itself. Because people often misunderstand what scientists mean when they say habitable. Habitable does not mean inhabited. It does not mean forests, oceans, animals, or alien civilizations. It simply means conditions where liquid water could theoretically exist for long periods of time. That's it. Mars was once potentially habitable. Venus may once have been habitable. Europa, one of Jupiter's moons, may contain a habitable ocean beneath its ice. Habitability is only the possibility for life, not evidence of it. And even that possibility depends on a terrifyingly delicate balance. TRAPPIST-1f. And the story changed once more. Planet F is almost exactly Earth-sized, but less dense. That lower density suggests the planet may contain enormous amounts of water. Some models estimate as much as 20% of the planet's mass could be water. That sounds exciting at first until you realize what conditions there probably look like. At that orbital distance, much of the water may exist as superheated vapor trapped inside a thick greenhouse atmosphere. Scientists now use the term steam world to describe planets like this. Massive atmospheric pressure. Intense heat retention. Oceans transformed into global boiling systems beneath crushing clouds. Not exactly ideal for life, but still scientifically fascinating. Because these worlds may represent entirely different planetary classes than anything in our own solar system. Earth has continents and oceans. Steam worlds may have global water envelopes thousands of miles deep with exotic high-pressure ice layers beneath them. Alien ocean chemistry. Atmospheric systems unlike anything humanity has ever experienced. The deeper astronomers look into exoplanets, the more they realize nature produces worlds stranger than science fiction. Then comes TRAPPIST-1G. Slightly larger than Earth. Orbiting near the outer edge of the habitable zone. 1 year lasts about 12 Earth days. The available data on this planet remains limited compared to the inner worlds, but scientists have identified evidence suggesting water exists in its composition. Whether that water exists as ice, vapor, subsurface oceans, or something else entirely remains unclear. But Planet G remains one of the more intriguing candidates in the system because it sits close enough to the habitable zone to potentially maintain moderate conditions under the right atmospheric setup. And finally, at the edge of the known system, sits TRAPPIST-1H. A small icy world orbiting farthest from the star. The amount of energy it receives is. TRAPPIST-1E is one of the most fascinating planets ever discovered because, despite orbiting extremely close to its small red dwarf star, it may still have conditions suitable for life. Although the planet sits far closer to its star than Mercury does to the Sun, TRAPPIST-1 is so faint that the planet receives only about 2/3 of the energy Earth gets from sunlight, placing it directly within the star's habitable zone where liquid water could potentially exist. The planet is slightly smaller than Earth and has a similar density, strongly suggesting it is a rocky world with a solid surface and gravity close to our own. These similarities immediately made TRAPPIST-1E one of the best candidates for habitability ever found outside our solar system. However, planets orbiting red dwarfs face major challenges because young red dwarf stars are extremely violent, blasting nearby planets with intense radiation capable of stripping away their atmospheres before stable conditions can develop. Scientists therefore focused on one critical question: did TRAPPIST-1E manage to survive this hostile early period, or was it left as a barren rock? Observations from the James Webb Space Telescope provided intriguing clues. Webb ruled out the presence of a thick hydrogen-helium atmosphere like those surrounding mini-Neptune planets, and it also failed to detect signs of a dense carbon dioxide atmosphere similar to Venus. These findings left open the exciting possibility that TRAPPIST-1E may possess a thinner, Earth-like secondary atmosphere dominated by nitrogen and potentially capable of supporting liquid water. Although scientists still cannot confirm whether such an atmosphere truly exists, the fact that it remains possible is historically significant. Some data suggest the planet could redistribute heat efficiently across its surface, while other interpretations point toward a cold, airless world. This uncertainty has made TRAPPIST-1E central to one of the most important scientific investigations of modern astronomy because if a stable atmosphere can survive around a red dwarf star, then potentially habitable planets throughout the galaxy may be far more common than previously believed. Researchers also suspect the planet could possess a magnetic field generated by a molten core, possibly sustained by tidal heating caused by the star's gravitational pull. Such a magnetic shield could protect the atmosphere from stellar radiation in much the same way Earth's magnetic field protects our own planet. If TRAPPIST-1E truly combines rocky terrain, stable temperatures, atmospheric circulation, volcanic recycling, magnetic shielding, liquid water, and enough time for chemistry to evolve, then the ingredients that allowed life to emerge on Earth may also exist there. The surface itself would appear alien, with a dim red star hanging motionless in the sky due to tidal locking, eternal daylight on one side, permanent darkness on the other, and a twilight ring where temperatures may remain most habitable. Nearby planets would appear huge overhead, while violent stellar flares would regularly erupt across the sky. Yet despite this harsh environment, TRAPPIST-1 continues to resist classification as a dead world. Scientists still do not know whether it hosts oceans and atmosphere or bare rock beneath a silent sky, but the search itself represents a turning point in human history. Humanity is no longer merely speculating about habitable worlds, we are actively studying their atmospheres, climates, and chemistry using advanced telescopes. Future observations may eventually detect combinations of gases such as oxygen and methane that strongly suggest biological activity. If life is ever discovered on TRAPPIST-1 or any similar planet, it would prove that biology emerged independently elsewhere in the universe, forever changing humanity's understanding of its place in existence.